Good to go.
Okay, great. Thank you very much. So good morning and welcome to all of our participants. And of course, a very special welcome to the Secretary General of CANTO, Mrs. Teresa Wankin. And of course, my colleagues, Daniel Fink and Nicholas Antoniello, who I will be introducing a little bit more formally later on. We are, the only way I can say this is we are extremely excited at what is happening today. And believe it or not, it has taken us over 8 years to get to this point. And I say that because I joined ICANN. My name, first of all, is Albert Daniels, and I am the Senior Manager for Stakeholder Engagement with ICANN. The acronym ICANN stands for the Internet Corporation for Assigned Names and Numbers. And what we do at ICANN is we work with several partners, CANTO included, to ensure that the internet operates properly and stably and securely. Now, a lot of the time, we don't really give a second thought to what's happening under the cover, what's happening behind the scenes. And you only think about that when it stops working or if the bandwidth is slow and so on. But what we do at ICANN is very critical work centering around something called the DNS, the domain name system, which translates domain names into IP addresses, which technically we will be talking about a little bit later on today. And the organization ICANN helps coordinate and manage that internet's unique system of identifiers by working with the IETF, working with organizations like CANTO and many other organizations worldwide. So my very first meeting when I joined ICANN over 8 years ago was actually a CANTO meeting. And from that time, I realized that CANTO is such an important organization that we need to find a way for ICANN and CANTO to work together. I think maybe a little bit before, around the time that I went to that first ICANN meeting, the acronym CANTO stood for the Caribbean Association of National Telecoms Operators. And I know Teresa will tell us how that has changed a little bit. And I don't think we actually use that expanded version of the acronym anymore. But the whole idea is that today what we have are representatives of our main ISPs throughout the region. I don't know all of the names, but I know names like Flow and Digicel, which are present in most of the islands and some others. And we are very excited and happy today to do this capacity building centering around the domain name system, because the domain name system is a critical part of internet infrastructure. And you, the persons in the trenches with the ISPs, are the ones who will actually ensure that we have a secure, interoperable, and stable internet. So just to mention a little bit more how we got here, there has been discussions going on between myself, Albert Daniels, and the Secretary General of CANTO, Mrs. Teresa Wankin, with regard to how we can work together. And this has been happening, like I said, for many years. I've been going to CANTO meetings. Teresa has been coming to ICANN meetings. And there was one time in Panama, we actually had the CANTO and the ICANN meetings in the same place at the Hard Rock Cafe. And this actually led to an interaction between myself and our technical team members, Nicholas Antoniello, who's the manager for technical engagement with our Latin American Caribbean group, and of course, Daniel Fink, who's the director for stakeholder engagement for Brazil, and a key person in the overall technical team to put this capacity building together in collaboration with CANTO. We have a very large shopping list of courses, but we selected a few of them for this particular event. So the key courses that we are going to be looking at for this event, this one, the Domain Name System 101, a general introduction to the DNS that we're starting today. We go, I think, for about 90 minutes today. And then we will go again on the 5th of July, looking at a technology that is related to the DNS, which is DNS security extensions, DNSSEC, which is a security layer that goes on top of the DNS. And then once we've covered all of the nice and interesting and boring theoretical stuff, then we will get our hands dirty by some real live hands-on labs on the 2nd, 9th, and 16th of August. Nicholas has put together a really fantastic tool that can be used virtually for doing labs. And he informs me that it is unbreakable. So you can do as a participant whatever you want based on what you've learned, and the system should not break. I see Daniel is laughing. I think he's made a bet with Nico to see if any one of the participants can break the lab. But I think it would be a good forum, a good system that we can use for actually getting to execute and try out the things that we are learning. So I'm really excited about having this capacity building today. I really am thankful to CANTO for making this possible. And it is now my pleasure to hand over to the Secretary General of CANTO, Mrs. Teresa Wanking, to make some of her remarks. So Teresa, over to you.
Thank you, Albert. Thank you very much. And good morning, everyone. I'm super excited to see these participants, over 140 participants registered. I know the others will join soon. We have 66 on with us this morning. So I'm really, really happy to see CANTO members, ISPs, taking advantage of this opportunity to build capacity and to strengthen the Caribbean Skills Bank. Your attendance this morning signals your intention to join an excellent lineup of knowledge experts in internet assigned names and numbers. When I joined CANTO and I learned about ICANN, I used to think, oh my God, those people are really bright to be doing what they are doing. All I want to know is how to use the internet. I don't want to know what makes it safe. I don't want to know what makes it reliable. I just want to know how I can use it, how I can benefit from it. So you guys here this morning are joining an excellent lineup of knowledge experts, Daniel and Nicholas, and even Albert. Make no mistake, Albert is a very technical person, technical to the bone. I ask him for advice when I need it at times. So you are in good hands this morning, and your attendance signals that you're now want to become a knowledge expert like them to adopt globally accepted protocols and standards so that you can build your networks, you can contribute to the Caribbean development in a better way. As we become more dependent on connectivity, this is one of the most sought after skill set. So I want to congratulate you this morning for making this choice. I also want to urge you to continue to take advantage of the opportunities being offered. In addition to this training, ICANN has a field of other training that you can benefit from. So in addition to participating in this, get to know the lecturers, get to know Albert some more, and get to know how you can participate in more of ICANN duty training and what they do. There are lots of networking opportunities as well. A little bit about ICANN, the internet, Albert went into it, but they are charged with the stability of the internet as we know it. And make no mistake, without the work that they do, what we know as internet would not be here. So be grateful for this opportunity and make sure you take advantage of it. ICANN and CANTO, as Albert said, from 8 years ago, have started to work closely together in promoting the safety of the internet and promoting the technical training and capacity building initiatives. And I'm really proud of this relationship that our members can benefit from. In addition to this training, if you have any particular training you want to see, technical training, of course, CANTO and ICANN is willing to consider how we can bring that training to you all, right? In addition to this set of training, Albert will tell you about the other training that ICANN do and how you can be part of that training. Building capacity in any organization is something that we should focus on more. A lot of times, the capacity building in the Caribbean is we go and we get training from international agencies, we get training, we go overseas for training, and then we come back. What do we do with that training? Do we use it? Do we transfer the knowledge? And do we build resilience among our peers with it? I want to urge you to take this training this morning to build your own resilience in what you do, and also to form your own networks. You're here with a lot of people from companies like yourself. Some of you might be competitors. So we would have some Digicells, we'll have some Cable Wireless, we'll have some Flows and TSTT, right? That's okay. You can network among peers. That is one of the things that Canto has built its strength on over the years. We bring all stakeholders together, and that's what ICANN is doing with us this morning, to bring all stakeholders together to build on a common good. So I urge you again to take advantage of it. Stay tuned to ICANN, stay tuned to Canto, and enjoy the training. Thank you very, very much.
Thank you so much, Teresa. We know that you are double booked this morning, but I know that you love ICANN so much that you
Yes,
made the time
and
to
I will
spend.
wait for Danielle. I am not leaving until I hear Danielle.
Yeah, so we really appreciate you taking the time to be with us, and also for working with our team to pull this together. So Daniel, I now hand over to you. And as I said earlier, for those of you who joined a little bit later, Mr. Daniel Fink is a part of the Latin America and Caribbean team. We have a small team, just over 5 persons who cover Latin America and the Caribbean, including Daniel, including Nicolas, who you would hear a little bit more from later on. And we all work together to ensure that you, the stakeholders in the Caribbean, are well taken care of. So it's my privilege now to hand over to Daniel, who can make his remarks and get us going this morning. Daniel, over to you.
Thank you, Albert. Thank you, Teresa. I fully agree. We are together, on these efforts, and it's our privilege to work together with you. I want to start by saying a big thanks to Cheyenne Williams and Charlene Richards. They who are CANTO officials. They helped us. They helped a lot us on spreading the word for this training. So we really appreciate their job. We saw the numbers in registrations coming up every day, so it was great, and we are just starting. We had some. I was telling to Teresa, we had some past experiences with this type of trainings. It's kind of more than 1 hour sessions each, and we will be together frequently. So we will have time to exchange a lot of things, but it is incredible how we can get close to you. We know you much better. You will know us much better. And then next time we see us face to face in the next event that Teresa and Albert will organize, I'm sure you'll have a lot of fun. And this is supposed to be interactive. We learn from you. Your questions are very important. Some things that you heard about DNS, you want to bring to the discussions, please do so. We have some little tools here. You can raise your hand at any time, open your microphone. So by the end of this training, we will be telling stories to each other, and this will be very meaningful. Okay, so thank you so much. Now I'd like to hand over to Nicolas. Nicolas, if you want to start, please do so. Thank you.
Thanks, Daniel. Well, hello everyone. I'm not sure. I think you are 1 or 2 hours, 1 hour behind, right? Behind my time zone, right, Albert? So here is 11:15. There should be 10:15, right?
That is correct, Nico.
Yeah, and a couple of Celsius degrees over my weather. Here is 7 Celsius degrees outside. So I wish I could be there face to face, enjoying the Caribbean weather.
You are always welcome, Nico.
Yeah, as soon as we can. This is gonna be face to face sometime. So because we are also kind of bored of this 100% virtual communication, let's say. So it's good to have the virtual, but not 100% of the time. So to start with, well, my name is Nicolas. I'm the technical engagement manager, regional technical engagement manager for ICANN the LAC region. So I cover all the Caribbean and the Latin American region as well. And part of Daniel, Albert, and a few other team members from the region. Feel free to turn on your cameras. Let's turn this into something less formal. Let's bring your coffee. If you want, bring your Coke, bring something stronger if you're allowed to at this time of the day. You can turn on your camera. This is meant to be the more similar to a face-to-face meeting as possible. So it's okay. It's okay to bring your coffee in the camera. It's okay to bring your dog in the camera, or any other member of your family if it's around that you need to bring it. So feel free also to open your mic and ask any question or any comment at any time. This is not an exposition. This is kind of meant to be for you and for you to ask or comment about your experience at any time. So yeah, feel free to do that. If you don't want to turn on your mic, or if you feel there's a lot of noise in the background and you want to write, just type your questions in the chat, and Albert or Daniel will stop me and we will read out loud the questions and try to answer them or the comments. And also you have the reactions here as Daniel told you, to say go slower, this is boring, go faster, whatever. Okay. First, before starting, I would love to do a kind of tuning for the presentation. So I will invite you to use the reaction button, the one that has a face in the lower part of your Zoom screen. You have probably in the right most, you have a reactions button. So I will love to turn thumbs up to all that are not so technically or do not deal with DNS servers in your day-to-day job. So all of you that are not so technical in your job tasks, or you do not deal with DNS servers, whether recursive or authoritative servers in your day-to-day job, please bring your thumbs up so we can kind of know all the people we are going to be exchanging ideas and talking to, and we can fine-tune the presentation so it's useful for everybody, whether you know a lot about DNS or whether you know nothing about DNS. So this presentation does not assume that you are an expert on DNS. So this is for everybody. We will try to level everybody to make everybody getting to know what the DNS is, why it was designed, what is its main function, and some add-ons that were added during this, let's say, 30 or 40 years, and how it operates to some degree. And we will continue with this in the next presentations. Perfect. Thanks very much. And let's start. I'm going to share my screen now, so you are not going to you're lucky because you're not going to see my face for a while. This is it. So I will ask Daniel and Albert if it's okay, if you are correctly viewing the presentation.
Yes, Nicolas, I'm seeing your screen, and while you're just about to start, can I ask the participants in the chat to just mention the names of the countries that they're from, so we get a sense of who we have, from across the Caribbean. Sorry for interrupting.
Excellent.
Nicolas, go ahead.
Excellent.
Yes, your presentation is fine. We can see.
Okay, let's start. So this is gonna be the not so basics of the DNS. Okay, you will see that we will skip some of the slides. Those slides, even if we are skipping them, they are going to be there in the presentation we are going to send to you in case you want to get deeper into some of the details. We are going to skip the most technical and not so relevant to the general knowledge about DNS, but they're going to be there. And of course, you can ask questions about them, now or after the presentation. You will have my email, Albert's email, Daniel's email, so we can contact us at any time to ask anything you want to know about this, and we will try to, of course, to answer you the best way. Okay, this is a little bit of story about the DNS and the internet. Okay, first, the internet is a network of networks. We often say that internet is that. It's a bunch of networks all connected together, into what we call a big network, and we put it a name called internet to that big network of networks. That big network we call internet. It's administrated by different organizations, enterprises, vendors, a lot of people. We at home can have servers connected to the internet and provide services or consume services. So all the users that connects to the internet are also part of that internet. All of those organizations and devices connected to the internet need an ID, need to be identified, uniquely identified, in order to reach them and to be able to exchange information. So what are identifiers internet uses? IP addresses. We call those identifiers are the IP addresses, same as in the standard or legacy telephony network. We use telephone numbers to identify the phones. We use IP addresses. IPv4 or IPv6 are two protocols that provides addressing for devices to be uniquely identified in a network. So we have IP addresses that identifies devices. And that's how internet started, and that's how devices exchange information among each other in the early days of the internet. But then someone came with this idea of we human beings. We do not easily remember number strings. Yeah, we do not easily remember. In my case, I hardly remember my phone number. So imagine having to remember an IPv4, which is 32 bits address, or IPv6, which is 128 bits address. Is huge. It's written in hexadecimal notation. So it's very, it's not useful to remember. So imagine if you want to access, I don't know, Google, or if you want to access Facebook or Netflix or your bank or your job web page or whatever, you have to remember the IP address just to access each and every single server on the internet. So that's not useful. People find it very easy to remember names instead of remembering addresses. That's why things like the telephony contacts exists in the phones. We remember the name and the surname of the person, and we have the phone associated with that name in that contacts database. Well, in the internet, these people came with this idea of creating a similar mechanism called DNS, domain name system. So what is the DNS? The DNS is a system that maps names to IP addresses. So we find it very easy to remember names, and there's a service called DNS that we translate those names into addresses that are the real identifiers that are used to, reach every single device, whether a server or just a client device connected to the internet. So there's literally billions of devices connected to the internet, each of them identified by a unique identifier, unique IP address, and you can create a name, associate that name with that IP to be easier to find or refer to that device. That's the DNS, okay? That's the simplest way of explaining what is the DNS. So the DNS maps names to numbers. We easily remember names, we hardly remember numbers, so we handle that to the DNS system, okay? Perfect. This is a little bit of history. In the early days, this mapping, this DNS database was just a file, a text file that has all the names, a tab or a space, and then the IP address associated with that name. Then another name, the IP address associated with that name, and so on. So you have a, you can easily find that as that file as those name to IP addresses definitions grow, that file can grow huge. So that actually does not escalate too much. So it's not a good way of storing information to store it in a single text file, especially if that is a huge text file, because you're gonna need a means to look at the whole file to find a name, then to see what's the IP address associated with that, and then to return that IP to the client or the one that is looking for that translation. So that was at the early days, a single text file, and you also have to copy that file into every single device that is connected to the internet. So that, again, does not escalate at all. So they came with this idea of having actually that file name. For those of you that are more on the technical side or remember this is the well-known among technicians, at least, file called HOSTS.TXT that exists on Windows operating systems and mainly all operating systems before the DNS. And as a legacy thing, this continues to exist, though it's not currently used, because it was taken over by the DNS. So now the system that translates names to addresses, it's called the DNS system, and it does the same. It translates names to numbers, but with a different, more scalable architecture and more distributed storage of the information, and also more distributed search for the information. So it's more resilient, more secure, and many other things that we are going to see in the next minutes. Okay, so the problems with the early host.txt file was, edits made by hand to a text file. No, it's not a database. No good. It's difficult to prevent duplicates. You need a means to synchronize the file among all the devices. That's we cannot think about that with the amount of devices we have now in the internet. That means a lot of traffic through the network to also, each time one new translation is added to the file, you have to redistribute the file to all the devices. So that's crazy these days. And it was also centrally maintained, so that is definitely did not scale. So we turn into the DNS, right? What is the DNS? So the DNS, it's a distributed database containing those translations from names to numbers. The architecture of the DNS, people that designed the DNS, think of the DNS database as what we call an inverted tree. So you see normally the tree, the root is at the bottom, and then the tree grows up. In the case of the DNS, the root is at the top and the tree goes down. So we have the root at the top, yeah? And then we have levels, what we call levels. Each level can have a lot of names. So there are names at each of the level, and there are branches that connects the root, which each names from what we call the first level, then branches that connects names in the first level with names in the second level. You see here is the root. You have the branches that connect the root with the first level of the DNS, which is, in this example, we have this UK, this com, this coffee, but you also have, .net, you have all the what we call the first level or top level domains. We are going to define that later. Then we have a second level. In this example, we have the foo, the bar, the example, and the branches that connect the first level to the second level, and so on. So each of the names of one level that connects to a second level name are called parents. And the names of the level below the parents are called childs, very original definitions. So we have parents and childs connected with branches, and all those form the DNS tree, starting from the root all the way down. Okay. Let's talk a little bit about DNS language we use. We call the root, and it's represented by a dot. A single dot represents the root, and it's the source of all the DNS tree. Okay, there is where the DNS tree starts. Then we have what we call first level domains. Those are the names in the first level. In this case, again, UK, com, and coffee. You see here, those are called top level nodes, top level domains, or first level domains. The correct name is top level domains, or TLDs, but by its English meaning of top level domains, right? The acronym. So then we have the second level domains. In this case, foo, bar, and example. We have the third level domains. Third level domains. In this case, there are three that are called the same, www, and there's one called mail. You will see that there's no problem in having same names for different nodes as long as they have a different father. So what could not exist is two nodes with the same name coming from the same father. Yeah, as long as they are childs of different parents, names can be the same. Okay. Then those names are composed by characters that could be letters, either letters, digits, or hyphen. No other symbol other from those three: letters, digits, or hyphen. Maximum length of a single name is 63 characters. And they are not case sensitive, so it doesn't matter at first. It doesn't matter if you write them uppercase or lowercase. It's no case sensitive as for the original DNS protocol. There may be some implementation of the protocol which is something completely different from the protocol that deals with the case sensitive, but that's not a good. That's not following the standard. The standard is not case sensitive. Okay. So every node has a name. That's what we call a domain name. Okay. So that domain name is built by how we build a domain, or what is a domain. Normally, a domain is not only the label of the node. For example, here, this example node has a name that is example, right? So what's the domain name? Is the domain name example? No, that's not the domain name. If you want to mention a domain name, you have to mention all the labels, all the nodes up to the root. Starting from the node you want to refer to, going up to its parents, then to the parents of its parents, and follow that path up to the root. As this is a tree, there's going to be only one path to the root, and only one path to the root. So it's going to be always very easy to follow all the path up to the root to form the domain name. So if we want to refer to this node called example, the domain name corresponding to this node is example, and we separate each of the labels with a dot, and we say, okay, if we want to refer to this node called example, this is example.com. The last dot the one that refers to the root can be mentioned, or it can not be mentioned as you wish, but you remember that it's always there. So we normally refer to this as example.com, and we skip mentioning the root because it's always there. In this case, this other node called www will be the domain name corresponding to this will be www.example.com. And in this case, this other www will be www.foo.com. So you see this domain www.example.com is different from www.foo.com. That's why you should mention all the path up to the root and not only the node label, because these two node labels are the same, but the domain is not the same because the path is completely different. Okay, so that's a domain. A domain is the label you are referring to and all the labels up to the root, separating them with a dot. That is what we normally call a full qualified domain name. And we will always refer to a full qualified domain names when we are giving a domain, when we are talking about a domain. Okay. Then that's a domain name. Okay. This is when things get a little bit complicated. That's a domain name. But what's a domain? Oh, wait. Is there any difference between a domain name and a domain? Yes, there's a difference between a domain name and a domain. A domain name is what we already said. The label, you read all the labels up to the root, separate them with a dot, and that's your domain name. But what's a domain? Okay, a domain is you take a certain node like this one, com, that has the com label, and the domain com, not the domain name, the domain com will be everything under that node. So all the tree beginning at that node down will be at the domain. So we are referring to com domain, all this, which is all the tree below below the com domain will be the domain for com. If we want to refer to the example domain, all these example and both of its childs will be, all of this will be the example domain. Okay, so example domain name is example.com. Example domain is everything, all the tree, starting from example all the way down. Okay, that's the difference between a domain and a domain name. And then we have a third definition we must remember, always remember, which is what we call zone. So what is a zone? We mentioned that the idea behind the DNS is that this database is meant to be distributed. So there's no going to be one and only one place where all the information is stored, but the information is going to be stored in many servers in different places. So we have a distributed database, not a concentrated one. Okay, and we will have organizations or entities in a more broader definition, entities that will administer that information. So the information is distributed and it's not administered by a single organization or a single entity, but it's also distributed in its administration. So what is a zone? A zone is all the part of the DNS tree that is administered by the same entity or the same organization. For example, in this example, yeah, as you see here, the title says zones are administrative boundaries. So we here in this example, there is this zone, the root is defined as one zone. This domain is defined as another zone. This one is defined as another one. This one is another one. This one is another. All of these three are another zone. These two are another zone, and these two are another different zone. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 zones in this example. But this could be divided in a different way, and we can say, okay, let's put all together in the same zone. Okay, then if all of this is administrated by the same entity, all of this will be within the same zone. It's just a matter of how you distribute the administration of the whole DNS system or the whole DNS database, okay? And that's up to the one that makes the division. And we are going to talk a little bit immediately about this, but I want you to remember those three definitions: a domain name, a domain, and a zone. Okay, so domain name is reading all the labels up to the root, separating them with dots. Domain is a node and all the tree under that node, and a zone is administrative divisions. All of the same nodes administrated by the same entity are within the same zone, okay, and are called a zone. So how you create zones? So the one that can always create a new zone is the father. In this example, the one that administrates the root will create zones. We typically create a zone, a separated zone for each first level domain. So each first level domain, each top level domain is a different zone. It's administrated by a different entity, okay? I think in future presentations, Albert and Daniel are going to told us about, how you can apply to have a top level domain and how those top level domains are created. We are not dealing with that in this presentation, but we have a huge and full, not so difficult, but it has some complexity process in order to be able to apply for a new domain, for a new top level domain. And if you go through all that process and you end up having been assigned that top level domain, what is going to be is that the one that administers the root zone will delegate that zone to you. And there you have a new zone in the top level of the DNS. So all of these, UK, COM, coffee, are different zones created and delegated by the father, in this case, the root. But each of the administrators of these new zones can create new zones, can delegate the administration of its childs or some of its childs to different or the same organization, thus creating new zones. For example, in this COM example, COM has created and delegated 3 zones, 1 example, 1 bar, and 1 foo. So this is administrated by one entity, this is administrated by a different entity, and this is administrated by a different entity. So we have 3 zones, three new zones. And it can be the same. Example could have assigned this WW and this mail to 2 different administrative entities and create 2 new zones, but decided not to do that and decide to keep this under the same administration. So keeping this under the same zone, okay? So I hope it's very clear what a domain name is, a domain is, and a zone is. This is very important. You should remember this. You should write down this, because these are the 3 main and most important concepts to understand the DNS architecture. Okay. Okay. If there are no questions so far, I'm not seeing the chat. So Albert or Daniel, if you can tell me if there are any comments or questions.
So there are no questions or comments in the chat right now, and for the time being, there are no hands raised. Okay,
so we're gonna start going a little bit, just a little bit faster now. Once we have these definitions clear, okay. Again, feel free to, turn on your mic and jump in at any time to ask any questions or make any comment. Okay. Then now we are going to talk about more deeply about how that structure, that database, it's distributed and sorted into the DNS system. Okay, so each of these zones that are administered by a different entity contains data. What data? Essentially the translation between a name and an IP address. Okay. So that is the data that is stored into each of those zones. And that is the data that is administered by the owner of or the administrator of the zone. Okay. That data it's stored somehow in a server. It could be a physical server, it could be a virtual server, it could be these days, it could be anything from a virtual to a physical device that stores the information for that zone. All the names and addresses that correspond to that zone are stored in that device within that zone. That file or database or whatever means you use to store the information is what we call the master file for that zone. Yeah, and the format, the way the information is written in that master file is what we normally call the master file format. And it has to do with the DNS standard. The DNS standard also defines how the information is stored, how the information is exchanged, and how the information is presented to the rest of the clients or the servers composing the whole DNS infrastructure. Okay, so there's something we call a zone file that will contain all the data for a zone in a master file format. So the zone file will contain all the translation from names to number, and the way that file is written, the way the information is stored, it's what we call a master file format. Okay. Let me advance the presentation. Okay. So that zone file, it's composed of what we call records. What is what is a record? What is a resource record? What is that we call a resource record in the DNS? The resource record is, imagine the resource record as a container that stores some type of information. So for each type of information you are going to store in your zone file, you will have a different resource record. Okay. We mentioned that the most common type of information we store in the zone file is name and a corresponding IP address. That is a specific resource record. There's a specific resource record to store that equivalence, that translation from name to an IP. But there are other resource records. We are going to talk about some of them in the next minutes. Okay. So different record types store or are meant to store different kinds of data. Okay. Where? In the zone file. So a zone file basically consists of multiple resource records. All the resource records for a zone file are stored in a zone file, in a different zone file. Each zone will have at least one zone file. There could be zones with more than one zone file in order to divide the data and make it easier to manage and deal with all the administration of that small part of the whole database, And this is very important. Resource records from multiple zones are never mixed in the same file. So there shouldn't be, and there's no same file mixing resource records from different zones. Okay. As every zone has at least one zone file, and there's no mixing of different resource records from multiple zones in the same file. Resource records have fields, so it has like labels that refer to the kind of information we store in that resource record, and also refer to other properties of that resource record. We are going to mention the 5 very quick. Normally, the resource record have what we call the owner label, which stores basically the domain name the resource record is associated with. So, for example, if you are talking about the zone file for com, top-level domain com.com, that the owner of that will be com, because that is the the name, the domain name associated for that resource record. If we have a resource record for nicolas.net, for example, the owner will be nicolas.net because that's the domain name associated with that resource records. It also will have a TTL, which we will talk about it later, but it's basically a timer. TTL is a timer or refers to a timer. It also has a class which is not used at all, or almost not used at all today, but it was defined in the original DNS standard, and it was meant to extend the capabilities and the functionalities of the whole DNS system. It also has a type label which says which type of resource record we are talking about. We will talk about this also later. And of course, it has a air data field, which is one of the most important fields of the resource records. That is actually where the data is stored. So that's the function of the record of the resource record, is to store information, and the information that is stored in that resource record, it's stored under the label air data within the resource record. Okay. Then this is kind of in a broader way, this is kind of the syntax. The resource record is in the master file format. So you have the owner, the TTL, the class, the type, and the air data fields, and all of these will correspond to a resource record. Okay. These are common types. You see, you mentioned we have a type label associated with a resource record. Okay, these are the most common types of resource record we will find in the DNS in a SOM file. So there's a resource record type called A record. An A record stores the translation from a domain name to an IPv4 address. So every time you will want to store the association or the equivalence from a domain name and IPv4 address, you will store it in an A type record. If we want to store the IPv6 address corresponding to a domain name, that's a different record, and we call that the record that associates a name with an IPv6 quad A record. So we have four A's to specify an IPv6 association with a name record, and an A for IPv4 associated with names in the DNS. Then we have what we call an NS record type, which stores the name of the authoritative server for a certain domain. We are going to talk later about what is an authoritative server for a domain. We have another record called SOA, which has information useful for the administration of the zone. We have a CNAME record, which is a record used to create aliases. For example, I can associate an IP address, an IPv4 address with nicolas.example.com, right? Imagine I have that domain, nicolas.example.com, and I want to associate that to an IPv4 address. So I have to create an A record that says nicolas.example.com corresponds to this IP address. Okay, but then imagine that I have other name that I want to link with the same address. Yeah, for example, nicolas2.example.com and nicolas3.example.com and nicolas4. And up to nicolas100.example.com. All those names, I want them to associate with the same IP address. So I have two options. Option one, I create all the A records, one for each name, associating them with the same IP address. So I have 100 different domain names, Nicolas, Nicolas1, Nicolas2, Nicolas100, all associated with the same IP address. That's one option. Or there's another option that makes it easier if I want to change the address. But because what? Guess if I want to change the address, I have to change the 100 records. Okay? That's another way of doing that. That is, I have one single record that says nicolas.example.com as associated with this IP address, and then I have Nicolas 2, Nicolas 3, Nicolas 4, Nicolas 100 associated with nicolas.example.com. So that's an alias. I'm creating aliases of nicolas.example.com, call it nicolas1.example.com, nicolas2.example.com, nicolas100. Those aliases are linked together. So if I have to change the IP that is associated with those 100 names, I just change one record. I change nicolas.example.com, and that's all, because all the others are associated with a name, not an others. Okay, so that's the way of that's why we have these aliases records and how we use them. Okay, that's a CNAME, an alias. We have MX record that stores the name of the email server for a certain domain. For example, if I run nicolas.example.com and I want to have a mail server, so I could create mail boxes under that domain. For example, I want to create administrator at nicolas.example.com. I'm going to give Albert an email under my domain. So I'm going to create Albert at nicolas.example.com. I'm going to give I'm going to give Brandon a mailbox under my domain. So I'm going to create Brandon at nicolas.example.com. Where do I store what's the name of the mail server for nicolas.example.com? In the MX record. So the MX record stores the name for the mail server for a certain domain. Okay, we will talk a little bit about that later. And then we have this PTR record that is used for what we call the reverse definition of the search, the reverse search definition. That is, normally we will use the DNS to translate from a name to an address. So normally we have the name and we want to know the address. Okay, but what about if we have the address and want to know about what's the name associated with that address? That's like the reverse search, right? So in the PTR, we store that information. The PTR stores the IP address corresponding to a certain name. This could be, someone could say, oh, but it's not the same. If we have a name associated with an address, it's not the same as having an address associated with a name. And the answer is no, it's not the same, because the reverse could be different from the forward. And this is when things get wild. Yeah, I can have nicolas.example.com associated with 1, 2, 3, 4 IPv4 address. And I can store that into an A record, because the A record associates a name to an IPv4 address. And I can also have 1, 2, 3, 4 IP address associated with something different from nicolas.example.com. And I store that in the PTR. Why I would do that? We are not going to, we're not going deeper into that, but yeah, you can have different differences between the forward and the reverse search. Okay, that's allowed by the DNS. Normally, you will want to map the same way, reverse and forward. So you create an A record that says certain domain name is associated with this IP, and then you create a PTR that says that IP associated with that same domain name. That's all. But you have to create both. You have to create an A record and you have to create a PTR record. If you have an A record, you can only search for the forward. If you have a PTR, you can only search for the reverse. So if you want to be able to search forward or reverse, you have to create the A and the PTR record, and DNS allows them to be completely different. Okay, that's up to you and your use case to create the same or to create them different. Okay, those are the most common resource records, but there are, up to today, there are around 87 types of allocated resource records. So here we mentioned just 1, 2, 3, 4, 5, 6, 7, and there are 80 more. We can talk about all week about these resource records. We are not going to, no, this is going to get very bored if we start talking about those at this point. Okay, so that's that's a resource record, and that's how we store information in the DNS database. Okay, in the master file, in the zone file, in the master file format. Okay, who defines which source record exists and how we use them? it is defined by a standard, which is created by the IETF standardization group, and it's maintained. The list of available resource records is maintained by the IANA, which is a decentralized office within ICANN. Albert can explain us a little more about ICANN structure in the future, which is not an easy. I think it's easier to explain DNS than to explain ICANN, some of the ICANN internal structure. I leave that to Albert and Daniel, and we'll stick to the DNS. So IANA, this ICANN office, basically maintains this this list of all DNS available resource records. So if you want to have a look at them, how they are used, and the format they have, and everything about them, you can go to this page, iana.org, assignments, DNS parameters, blah blah blah, and or just say for IANA DNS resource record types, and you will be probably taken to this page. You have all the resource records. Some of these we already talked about. You have the number assigned to them, because all of the resource records have an assigned number to be able to differentiate from among them, and you have the meaning, what is that name or type referred to, and the RFC, the standard that defines how we use and what kind of information that resource record stores. Okay, that's all about resource records. So let's talk about some of these resource records in more detail, but we will not talk about all of them. I will take one or two as an example, and then you can go through the rest and ask any question in the future after this presentation, or wherever you have time to have a look at this and desire to have a look at this. Okay, so we will talk about A and Quad A resource records. We mentioned that the A record, it's designed to store the association of a domain name to an IP address. So I have the domain name and I want to know the IP address. This is stored in an A type record. Okay, so this is the most common use of the DNS, is for mapping domain names to IP addresses. If I want to map a domain name to an IPv4 address, I use the A record. If I want to map a domain name to an IPv6 address, I use the Quad A record. Okay, so A record maps domain names to IPv4 addresses. This way, this is a definition in a zone file. This is the definition of a record. We put the name we want to associate with the IPv4 address. Then we make a space here, and we put the type of record we are going to create. This is an A record. And then, as this is an A record, it will be translating a name, a domain name, into an IPv4. So I need the IPv4 associated with this name, and that's all. On the other hand, if we want the IPv6 associated with this name, we have to create another entry with a different record type called Quad A, and we say, okay, example.com, same name, but now I'm going to create a Quad A record, and I'm going to associate an IPv6 address. So now this name has two associated addresses, one IPv4 and one IPv6. So if I want to access this, a server that has this, has assigned this domain name by its IPv4 address, I will ask the DNS system for the A record associated with that name. If I want to access the server by its IPv6 address, I will ask the DNS system about the Quad A record associated with that name. Yeah, that's simple. Okay, this is how we use and how we define A records and Quad A records. Okay, this is DNS record. What is the NS record? We mentioned that NS record specifies an authoritative server for a zone. So what is an authoritative server for a zone? Okay, the authoritative server for a zone is the actual server that stores all the information, all the data for that specific zone. Then, if you are talking about nicolas.example.com domain name, and we create a zone, that I will administer because it's my server, and I will create an authoritative DNS server with all the data associated with nicolas.example.com. I will put all that data into my server, into a zone file I create into my at my server. So how this works? So I will need a server, whether virtual or physical. I will install a DNS server software there. I will create a zone file for that zone, nicolas.example.com, and I will put all the information related to that zone into that file. How I will put that information? Creating different resource records. For example, I'm going to create under nicolas.example.com, I'm going to create a web page. And I'm going to assign it the name www.nicolas.example.com. And then I'm going to assign an IPv4 and IPv6 address to that web page. So I'm going to create within my zone, I'm going to create two records. I'm going to create an A record for the correspondence www.nicolas.example.com A, and then the IPv4 address of my web server. And then I'm going to create the same www.nicolas.example.com, quad A, and the IPv6 associated with my web server. And I can add as many records as I want in my zone file. And that will be the zone file for nicolas.example.com. Okay. There's a record that stores what's the name of that server, because I will have to assign the DNS server where this DNS software runs needs a name. So guess what? I'm going to call it dns.nicolas.example.com to be very original. So I'm going to call my DNS server dns.nicolas.example.com. I have to create an NS record that says nicolas.example.com NS, and then I said dns.nicolas.example.com, or as it's shown in this example, the name server for example.com, it's called ns1.example.com. And there's a second DNS server for the same domain, example.com, for the same zone, that is called ns2.example.com. Why would someone have two different DNS servers for the same zone? Well, to be more resilient, to have more redundancy, in case one of the servers fails, you have the other. So if someone is trying to reach information you store in your zone file in this server, but this server, I don't know, lose powers or shut off, or its processor or hard disk breaks or whatever happens and goes offline, you still have this one that has the same exact information. So all those that were carrying this server will now carry this one, and they will get the same answer. No one will notice that one of those it's down, and they will still be able to get the information. So you can create as many servers for your zone as you want. The more you create, the more resilient you are and the more redundancy you have. Of course, the more you create, the more administrative tasks you are creating. So there's a balance. There should be a balance in the number of servers you have for a certain zone, if you don't want to, get crazy about administer a lot of servers. But it's always recommendable, and it's a good practice to have at least 2 authoritative servers for a zone, at least 2. Okay, the more the better, but the more administrative tasks you will need to know to do. Sorry. Okay, so that's the NS record. The NS record maps or stores all the names of the named servers corresponding to a certain domain. Okay. This is the way DNS we talked about the way the DNS makes delegation. The way that we create zones in the DNS is by the parents delegating in their child's. So in this case, the root has created and delegated one zone called the .com, and then com can create zones, can delegate the subtree under com to the same organization. It can keep all of this in the same com zone, or it can create, for example, one zone for these two called foo.com, one zone for these two called bar.com, and one zone for these three called example.com, right? And assign each of them to a different entity. So it's creating three different zones. And the administrator of each of these zones will have its own server, which is with its own zone files, with its own records within that different zone files. Okay. This is already we already talked about this. We will skip this. There's something that is called a glue record. We will talk about this probably in future presentations if we go deep into how to administer and how to install and how to develop an authoritative server. Okay, we will skip this for this presentation. Okay, then we have other type of record, which is called the SOA. The SOA, I would only say that the SOA will contain administrative information about the zone. So there's each zone file, it's going to have one and only one SOA record that will contain information about that zone. Okay. What kind of information will it will contain? Information in order for the DNS system to be able to administer that zone. So this is going to be used for internal use of the DNS system, and it's meant for zone administration. So the information containing here is things like the serial number, the refresh time, and other fields that we again will talk on. We'll get deeper into this when we talk about authoritative server administrations and the creation of zone files. We will leave this also for this presentation, but it's good for you to have all of these, resource record types explained here. We already talked about the CNAME and how it's used. We already talked about the MX here, small detail about how it's used and how it's defined. We also talk about the PTR, which is the reverse the record meant for reverse search in the DNS, and it refers to a whole separated tree created in the DNS infrastructure under the in.addr.arpa domain. So we will get deeper into this in future presentations also. Okay, you have all a brief explanation of all the basic resource records we already talked here in the presentation. I will leave that for you to have a look, and if you have any question about that, we invite you to send us any comment or questions, and we will try to answer it. Okay, so we've talked about what's the DNS, how the DNS is created in this structure that looks like an inverted tree, how the information is stored in that database. Okay, and then how it works, how the DNS works. We now have a lot of servers distributed in different zones. We created each of them having a zone file with a lot of information, translating names to addresses and other stuff, and how we use that. Okay, so the DNS system has mainly two kinds of servers. There are servers called authoritative servers. We already talked about them. Authoritative servers are the servers that stores the information for each zone. Authoritative servers are the server that has the zone files that, again, they have all the records corresponding to that zone file that is stored in the authoritative servers. And then we have another kind of server that is called name resolver, sorry, that's called resolver, yeah, or recursive server. Sometimes we call it resolvers, sometimes we call recursive servers. It's the same. It doesn't matter if you call them resolvers or recursive servers. We are referring to the same kind of server. And what's the task of a resolver? What does resolver do? Okay, resolvers are in charge of searching for the information in behalf of the clients. So if I have my device, yeah, I want to access a web page. Let's say I want to access Amazon web page. Okay, I have www.amazon.com. Okay, I need the IP address. My device needs the IP address in order to reach the server and, you know, pull the web page. What do I do? The same device goes and asks each and every authoritative server out there searching for the IP address corresponding to www.amazon.com? No. It will handle the query, it will handle the task to a resolver. My device will send the task, will send the query to a resolver, will say, hey, resolver, I want to know the IP addresses corresponding to www.amazon.com. Make it happen, do all the magic, and give me the IP. I won't do that. You do it. Okay. The resolver is the one that is going to search for the answer, carrying in turn some authoritative servers until it finds the authoritative server that has the IP address corresponding to www.amazon.com. Once it has that answer, it will bring back the answer to the client that asked for it. Okay, so resolvers are the one in charge of searching for the information, and authoritatives are the one that actually stores all the DNS information. Okay, we have those two types of servers in the ecosystem, in the DNS ecosystem, and I mean, all of them needs all of the others. There's no DNS without either resolvers or authoritative servers. You cannot run a DNS system with only resolvers, and you cannot run DNS systems with only authoritatives. You need both of them. Okay, we'll talk about some other aspects of authoritative and resolver servers later. So now we are going to see how this resolution process works. Okay, let's go again. Let's go back to the example we were talking about. We have this client. In this case, it's a phone. It's someone opens a browser in the phone and wants to access some web page. For example, let's say we want to access www.example.com website. Okay, so what is going to happen is that our device, actually the browser in our device, it's going to call an operating system built software that is called a stub resolver, which is actually a DNS resolver. That that DNS resolver within the operating system of the device will have the only task to send that query to some resolver out there. So the resolver of the device, stub resolver of the device, will send the query. In this case, what I want to know is the IP address corresponding, IPv4 address corresponding to www.example.com, will send that query to a recursive name server, to a resolver, to a DNS resolver. That resolver, that DNS resolver, will start asking different authoritative servers until it finds the authoritative name server that has that information, will get that information and will bring back the information to the device that asked for that. Okay, let's see how it works that in more detail. Okay, so let's go straight to the example. Okay, and here our example, here is where our example starts. Okay, we have this device, the browser, the stub resolver. The browser wants to access www.example.com webpage and sends that query to the stub resolver asking for the IP corresponding to that domain name. The star resolver will send that to a recursive resolver defined by the normally this is if this is a home client, for example, an end user client. This is normally this recursive resolver is normally defined by the ISP, the internet service provider of this client. So the organization that provides internet access to this user or to this device will tell the user, okay, if you want to do DNS resolution, use this resolver, and it gives you the IP address. Of course, it can't give you a name, because if not, we get into a problem of egg and chicken. You know, if we have a name, we will need the DNS system to resolve the name. But if we are talking about the resolver, we need the address, because we don't have a DNS system to ask to. Okay, so the ISP typically will give you will assign you and will tell you which resolver to use. So this star resolver sends the query, what is the IP address of www.example.com to this recursive resolver. Okay, this recursive resolver has to find the answer. So it has to find the IP corresponding to www.example.com. So it has to query authoritative servers till it finds the authoritative server that actually has the information, that is the owner of that information. How the recursive resolver finds that information? Okay, it can happen, two things can happen. One is it can happen that the recursive resolver previously had the same query and solved it and found the information for that query. And it could happen that it already has that information. It already has that information in its memory. The resolver can memorize stuff that already found in the past. So if the resolver has that in memory, it will straight bring the answer give the answer to the client with no search at all, because it searched for it in the past. It has it in its memory. It will give it from the memory. That memory is what we normally call the cache of the recursive resolver. So recursive resolver has cache. What is cache? The ability for the recursive resolver to memorize past queries. Okay, but for the sake of this example, let's pretend that the recursive resolver just started to resolve, so it has nothing in its cache, nothing in the memory. So it gets the query from the client and has to solve it. Who is the first authoritative server in the whole DNS system that the recursive resolver is going to query for this answer? Well, recursive resolvers always start by querying the root servers. Yeah, so recursive resolver is going to handle the query to a root server, and there are many root servers we are going to talk about later. You remember that we said that for a specific domain we can have as many name servers as we want. We can create as many NS records as we want. We already said that. Okay, for the root, the beginning of the DNS, there are many servers that answer the same information. All the servers for the same zone should have exactly the same information. So any resolver can ask any of those servers and will get the same answer, no matter which of those servers ask. So we said the recursive resolver will always first ask a root server. It's going to go to the root, to the dot, to the beginning of the DNS tree. And it's going to ask, hey, root server, I want to know the IP address of www.example.com. And the root server, of course, is not the owner of that information because it's delegated to someone else. But when an authoritative server is not the owner of the information, it won't answer, hey, no, I don't know that. No. Authoritative servers always answer the best they can for the recursive resolver to find the owner of the information. What is this? How this works? Okay. The recursive resolver sends the query to the root server asking for the IP address for www.example.com. we said that the root server is not the owner of that information, but the root server, the dot, is the father of the com, because the com is a first level domain and the root is the father. So the root knows who is the owner of the com zone, because the root delegated that. And the root has an NS record for that. So the root will say, hey, I don't know that answer. I don't know what's the IP of www.example.com, but I could give you the IP of the com authoritative server. Go and ask him for that information. Maybe you're lucky. Okay, so the root server will respond to the resolver. Here are the name servers for the com. Go and ask them. And the recursive resolver now knows who is the authoritative server for .com. And guess what? It's going to ask the root servers, it's going to ask, sorry, the authoritative servers now of .com the same question. Resolvers always ask same question, exactly the same question. But now to a different server, to the authoritative for .com. Hey, authoritative for .com, what's the IP address of www.example.com? The authoritative for .com is not the owner of that information, but is the father of example.com, because example.com is right under .com. So .com knows who is the authoritative for example.com, because it delegates it. So in this case, the authoritative for .com will answer the recursive server with here are the name servers, or here is the name server for example.com domain. Go ask him. Okay, the recursive so say, okay, no wait, I'm gonna ask this new authoritative server. So we are getting closer to the answer, right? The resolver now asks the same question again. What's the IP address of www.example.com to the authoritative of example.com? And guess what? Now we are asking the authoritative of example.com about www.example.com. So in this example, this authoritative server is the owner of that information. So the authoritative server for example.com has the translation, the association for www.example.com to an IP address. As it's the owner of that information, it will answer with the information, it will give the information to the recursive resolver. So in this case, the authoritative for example.com will tell the recursive resolver, here are the IP addresses, or here is the IP address for www.example.com, which is exactly what you're looking for. So now the recursive resolver receives that answer and says, hey, I got what I was looking for. And thus, and the recursive resolver is going to do two things. First, it's going to store that answer in its memory, in its cache, in case in the future, the same device or any different device asks the same question. So it doesn't have to go out and search for it again. I already searched for it. I store it in my memory. And if someone asks the same, I already have information. And the second thing and most important thing the resolver is going to do, of course, it's going to give the answer to the client that was seeking for that answer. So now the client has the IP address corresponding to www.example.com. The stubs resolver will give that answer to the browser, and the browser will be able to pull the web page from that server. Okay, and that's the end of the DNS resolution. And that always happen, almost always happen at the beginning of any exchange of information from any device in the internet. Almost all exchanges of the information, mainly with public servers in the internet, starts with a DNS resolution that works exactly this way. Okay, once we have the IP address, we do the rest of the stuff. In this case, pulling a web page from a server, but we need the IP address for that. Okay, so you see the importance and how critical is the DNS service for the DNS to for the internet to be able to be searchable. Let's say, is internet going to stop working if DNS stop working? No, Is there anyone going to be able to use the internet if the DNS stopped working? No, because nobody remembers the IPs. And the system that translates them, the names to the IPs, is the DNS. So if the DNS stops working, internet won't stop working, but we won't be able to use it. So it's more or less the same, right? Here you have a second example where a different device now asks for ftp.example.com, and the recursive resolver, you remember that it caches everything that gets from my authoritative servers, put it into the cache. So the cache of the recursive resolver does not have the answer for this, but it has in its cache, which is the authoritative.com, which is the authoritative of example.com, and what's the IP for www.example.com. As now the recursive resolver is looking for ftp.example.com, it won't ask the root again. It will go straight to the authoritative of example.com. So the resolver skips most of the search of the resolution process and go directly to the example.com authoritative server and say, hey, authoritative for example.com, tell me what's the IP for ftp.example.com. Example.com will answer with that, and recursive resolver will put this in its cache and also will give it back to the client. So you see now how important is the cache to speed up internet, to speed up a DNS resolution, right? Someone could ask, hey, but what about if your resolver has put something in its cache and then someone at the authoritative server changed that association? What about if the IP associated with ftp.example.com changes? If the resolver is not going to ask again and is going to take it from its cache, it's not going to be aware of that change. So things are going to start failing because the association that the recursive resolver has in memory is wrong because the IP changed it. Well, guess what? The recursive resolver puts things in its cache, but assigns a timer to each of those entries in the cache. So each entry in the cache, each entry in the memory has a timer. Once the recursive resolver puts something in memory, puts something in the cache, it triggers a countdown from a certain value down to 0. When that countdown, when that timer associated with that entry reaches 0, the resolver will delete that entry from its cache. And next time someone asks the same, guess what? The resolver won't have that in memory and will have to go again all over the resolution process again to find the answer. So,
excuse me, Nicolas.
Yes.
We have a question in the chat from Luciano Johari from Suriname. Yeah. I think what he's asking is, what is the response time? So I guess possibly he's asking about the response time to query the root server and then recursively go down.
Yeah.
So perhaps you can respond to that. And then there's another comment from Vivek. So let's deal with Luciano first.
Yeah, trying to answer Luciano's face, it depends. The answer, the fast answer is it depends. The response times will depend on how close you are in network terms, how close you are to each of the authoritative servers you have to query, and also how close the client is from the recursive resolver it's using. For example, if this device is my phone here in Uruguay, my recursive resolver, we suppose that it's run by my ISP, so it's very close to me. It's also here in my same city in Uruguay, so this is kind of this time, the round trip time and the time this resolver takes to process my query. It's kind of a few milliseconds, like 1, 2, 3, 4 milliseconds, but it's very fast. But then if these root servers are for example, in US, and the authoritative servers are in Europe, the rest of the authoritative servers are in Europe, this information has to travel a long distance in order to reach and to complete the whole resolution process. So the whole resolution time, if you add all of those trip times, it can vary from almost 0 milliseconds if everything is close, or if the recursive resolver already has the answer in its memory. This is going to be very fast because I query the recursive resolver. The recursive resolver look at its memory. It has the answer and answers me. This could be like 2 milliseconds, 1 milliseconds, or even faster, even 0 milliseconds. We're a fraction of milliseconds. But if it has to go through all of this resolution process and the servers are located very, very far away from the recursive resolver, this could take time because information travels at light speed, but light speed is not it's not infinitely fast. It has to travel. So this could vary between a few milliseconds and a few hundreds of milliseconds. For example, in average, if I'm located in Uruguay and want to resolve something that is located in the US or in Europe, it can vary from 150 milliseconds to 300 milliseconds could be. It depends on how much this information has traveled and how fast these servers respond to the query and how fast the recursive resolver process the information. Normally, the time consumed by the servers in processing the information is, we can consider it 0 because it's very, 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 very short compared to the travel time. What defines here the whole time is the distance, the network distance, how far the devices are one from each other. Even at light speeds through fiber optic networks, this can take a few hundreds of milliseconds. If it can take up to a second. It's very strange, it's very rare, but it can take up to a second. So that's why to have a good cache strategy in recursive resolvers is very important. That is why recursive resolvers actually have a memory and memorize stuff. And that's also why it's important to keep the root servers and the rest of the servers as closer as I can from my resolver. And we will, in future presentations, we'll talk a little more about how to speed up the DNS resolution process. So how to, bring those numbers down to a few milliseconds. From
okay, so sorry to interrupt again, Nicolas. There are a few more comments. I guess when you were talking about how long the information stays in cache, somebody, what's his name, Vivek, made the comment TTL.
Yeah,
Vivek
was think, right about the TTL. That is exactly the timer that is going to be associated with the cache entry.
Right.
Yeah.
And then we have another question from Raymond Khan, who I think is in Guyana, but he's asking, does Suriname have an instance of a root server? And I guess Sean Duncan is asking the same thing about Belize.
Yeah,
so perhaps you can respond to them.
Allow me a few minutes. We are on the top of the time window we have, but I'm going to go very fast from here. I'm going to talk about a little bit to cover that. I'm going to talk a little bit and very fast about DNS resiliency. So we mentioned that we can have as many authoritative servers for a certain zone as we want. Okay, we can have. It's recommended to have at least 2. So we need 2 NS records, or we can have as many as we want. We can have 10 authoritative servers, all of them containing exactly the same information. So a resolver can query any of them and we'll get the same answer. Guess what? If you are running 10 servers for the same zone, you will want to physically put those servers distributed all over the world. So resolvers will have at least one of those authoritative servers that contains all the same information closer. That happens for any authoritative server. In particular, that happens to the root servers. So if we have root servers distributed all over the world, it's likely that the resolver is going to be closer of a root server. And the closer the resolver is to the root server, the shorter time this first query, sorry, let me go back. This first query will take. Okay. And that's the what happens in real in the internet. So let me give you a fast root zone administration screenshot to answer to those questions, and to also end up with a presentation, and also as an example of having more than one authoritative server for the same zone. This we are going to explain for the root zone. It's equivalent for any zone. You can have as many authoritative servers for a certain zone as you want. We are going to put the root as an example of this, because this is what actually happens. So people that designed the DNS, and from the beginning of the DNS, the administration of the root zone, the organizations that administers the servers that stores the information for the root zone, are 12 organizations. So the ones that, when at the time when the DNS started, the administration of the servers that serves the root zone was given to 12 different organizations. Yeah. And you say, oh, these are and each of those organizations was assigned one letter. In real, it wasn't the organization that was assigned the letter, but it was the instance of the root server that was assigned a letter. And you can say, hey, you are saying that there were 12 organizations, but here there are, 13 letters. So why 13 letters and for 12 organizations? Well, if you look carefully here, you see that this organization called VeriSign has two instances assigned, the A instance and the J instance. Okay, so there is one organization that has two instances assigned, and the other organizations have one DNS root server instance administration assigned. Okay, so what does this organization do? This organization have a copy of the root zone in their server, identified by this letter. So this is the A root server, this is the B root server, this is the C root server, and so on. And each of those servers has a copy, the same exact information, the same exact copy of the root zone. Okay. And to complicate a little more, slightly a little more, each of these organizations uses a technique called Anycast that allows for further replication of the root zone. Anycast is a technique that allows two devices in a network to share, to have the same assigned IP address, and say, hey, you've gone crazy. At the beginning of this conversation, you said that all the devices in the internet should have one unique IP address in order to be able to reach them. Yes, that's true. So what happens if we put two or more devices in the internet, all with the same IP address? What device are we going to reach? We don't know what device are we going to reach. It's the network that is going to decide which device, the one that is closer, for example, is going to reach. Well, guess what? That doesn't work in most of the cases, but if all of those devices, all of those servers have the same information, it works, because if all the servers have the same information, you don't care about which of those servers are you reaching. All have the same information. So that's a use case when it's useful to have the same IP address in more than one device in the internet, as long as all the devices serve the same information. DNS, it's a case of that. In the DNS case, all of the copies of the same root server have the same information. They all have the root zone, a copy of the same root zone. So you can assign the same IP address to as many root servers as you want, and you can replicate and distribute them all over the world. So at the end of all of this, this is a map that is kept by this organization, rootservers.org, that builds a up-to-date map of all of the root server instances that are out there. Each of those instances is a copy of one of these 13 instances. So we have 13 instances originally assigned to one of these organizations and run by these organizations, and then each of these organizations created by using the Anycast technique created lot of more copies, ending in this. And this is a screenshot I took 2 days ago. No, yesterday. This is a screenshot I took yesterday, and yesterday at 9 p.m. my time, Uruguay time. No, this is UTC. So yesterday at 9 UTC, the root server system consists of 1,610 copies of the root server operated by 12 independent root server operators. Okay, so how many root servers are there? Are there only 12 root servers? No. Are there only 13 root servers? No, there are 1,610 root servers out there distributed in big numbers like this here, all containing the exact same copy of the root zone. This is assuming in the Caribbean and Central American region. So there are apparently many servers distributed. You can go to this rootserver.org website, and you can zoom and continue zooming in the map, and you'll see how these 4 are distributed and exactly in what city, what country these servers are located. So a resolver, say in, I don't know, in where Albert, choose a country in the Caribbean region.
Okay, let's say St. Vincent or
okay, so
or Grenada.
Or Grenada. If we are talking about St. Vincent or Grenada, and if we are talking about a resolver located in an ISP, in an internet service provider in St. Vincent, in the first step of the resolution process, it has to reach a root server, right? It will probably reach one of these 9 root servers that are very close to that resolver. That will speed up. It will take a few milliseconds to reach one of these 9, compared to hundreds of milliseconds only to reach these root servers based in Australia, for example. So this is how important it is to have distributed all the root servers in the whole world, because the root servers are always where the DNS resolution starts. So every resolver always starts by querying a root server. Okay.
So Nicolas, I have a really nice question from Faber in Belize. What would happen if the IP in the resolver cache is different from the server IP and the countdown has not finished?
That's an excellent question. You are screwed. Basically, we are in Houston, we have a problem. The resolver will receive the query from the client. Hey, give me the IP of www.example.com, and the resolver will say, oh, let's see if I have that in memory. Oh, I have it in memory, and it will answer the client. This is the IP for www.example.com. But guess what? The owner of the zone changed that. So the real IP is not that one because it changed it, but the resolver isn't aware of that change because it didn't went through all the lookup process. It already has the information. It takes it from the memory. So it will give in that during the TTL, during that countdown, if someone asks for information that it's in the cache, but also has changed it, the resolver will be answering wrong question to the clients, and the clients won't be able to access that resource. That's the simple reality. So that means that every time someone changes an IP addresses, there are going to be a lot of wrong answers and a lot of people not able to access sites or resources. No, because there's a process, there's a good practice to when you are changing the IP of a domain. If you're, let's say you run a web page, let's say you have a server with an IP, let's say you say, oh, this is this host hosting service is charging me a lot of money. I'm changing the hosting, and you change to, let's say, a different continent or a different country with a different hosting provider with a different IP address. So now your website, www.example.com, has a different IP address. So you have to change the DNS entry for your website. What happens with all the resolvers that already have that in memory during the time you set the TTL? Okay, the nice way to do that is you keep the old service up and running with the old entry, with the old record exactly as it is. You don't change anything. You bring up the new service and you create a new entry that says the same name has this new IP address. So now you have www.example.com, a record to one IP address, and the same name, a record to another address. So you have two servers for the same web page. That's no problem. There's going to be some people that is going to still be reaching the old one, and some people that is going to be reaching the new one, right? Then what you do, you delete the old record. So you will only have one record, the new one in the DNS system. You will have your domain name, a record, new IP. That's the only record that is going to exist in the DNS. But you do not put down the old site with the old IP. Till when? You wait for the TTL to go down to 0. The worst case would be someone that just asked for that. So if you know your TTL is 1 hour or 1 week, you will have to keep both sites up and running for 1 week, the old one and the new one. The DNS will only have the new one, but the old one will be up and running, still up and running. So all those that in memory are going to be taken to the old service will still work. Once that TTL goes to 0, you put down the old service, you end the relation with the host provider in our example, and you have the new site up and running, and no one noticed that you changed anything because everything was smooth. That's a smooth transition. If you put down the old one and you bring down the new one, you are screwed. You will be probably many people will try to reach the old one because of the cache of many resolvers out there. Okay, hope that answers the question. Yeah.
This is Daniel. Can I share one quick questionnaire with all of you?
Yes. This is by the way, this was the end of the presentation. Of course, if you still have any question, you can throw it in the chat or maybe contact us later. Hope it was interesting for all of you. It may happen that some of you already know about this and you are a little bit bored and you are very happy this end and you can go to have lunch. I hope even you know about this, you enjoy it, and I hope it served as a recap of everything you already know. And I tend to see this as a leveling first presentation. Next one, we are going to go into the DNSSEC, which is a little bit more tricky than this, but a very far more interesting. And it's a kind of security add-on to the DNS system that is basically what we talked about today. So thanks very much for sticking with us a couple of minutes more than expected, and feel free to start answering the poll that Daniel just pop up, and yeah, feel free to reach us in the future as many times as you need to with any question related to this or to any other topic that falls within ICANN remit. Thanks very much. Have an excellent day and have an excellent and delicious lunch. You deserve it.
Yeah, this question, we have two questionnaires. This is the first one. This one will be helpful for us to prepare for the next session. This is not evaluation, just some feedback for us. And as soon as we have at least 50% of you filling up this one, I'll share the the next one, which is about the overall training, to see to what extent this was useful for you. So far we have 34 answers, 36%. It's coming up. So many of you are not sure about which types of DNS servers you have, which is okay. Many of you have recursive and authoritative servers. This is good. You have your own servers. Good news as well. 61% have your own servers.
By the way, Daniel, someone is asking if the video and the presentation for this presentation,
yes,
redundant is valid, is going to be sent to them. Of course, this presentation is going to be sent to you, and the video will be available as soon as Daniel or Albert, I don't know who is the master of the Zoom session, ends the Zoom session, and Zoom does its magic, and we be able to send you the link to the video. But yes, presentation and video is going to be available for you to check and see our phrases as many times as you want in the future.
Yeah, thank you. Yeah, we reached the 50% responses. Thank you. So I want to bother you for this last one, which is about the evaluation of this training. To what extent this is useful for your work, and if Nicolas did a good job or not, please let us know. It's completely anonymous, don't worry.
Just Nicolas's address is also posted. Nicolas, I just put your email address in the chat for anybody who wants to overload your mailbox with questions.
There's a question from Matthew that says, does the IPv6 DNS now have backward compatibility to IPv4? The first answer is yes, yes, and yes. All actually, and from many years ago, all DNS servers are capable of serving content using IPv4 or IPv6, and are all capable of creating the authoritative servers, A records or quad A records since the beginning. So it's, almost 30 years this is possible. And in the real life, there are still some DNS server administrators that have not implemented IPv6 in their servers, and that's one thing that we encourage, really and seriously encourage every DNS operator, whether they operate a recursive or an authoritative servers, to run them both IPv4 and IPv6. So the servers are being able to reach them using IPv4 or IPv6 by any client. Okay, but the servers are supported. It's just the administrator has to implement IPv6 as well as IPv4, but it's all functional and compatible.
So we are pretty much at the top of the hour. Thank you very much, Nico. Thank you all participants for engaging with your very useful and interesting questions. At this point, I hand back over to Daniel to bring the session to a close and remind us of what happens next.
Okay, thank you very much, Albert. So we have our next session. Please help me to remind, for July the 5th, DNSSEC. July the 5th, yes. So please make sure to register. I will send you reminders about the Zoom room before the training, one day before the training. So, and we will keep in touch. And if you have any other feedback, please feel free to email us. You have my email already from the invitations, and Albert shared the emails here. So that's it. Thank you so much. And
Daniel,
yes,
just to set some of the expectation for this 5 presentation series, the idea at the end of this 5 presentation series is not only that you know what is DNS and all this sometimes boring theory stuff, but also for you to be able to fully install from scratch, configure and operate DNS resolvers using all of what we will review today and in next presentations. All of those resolvers, you will be capable of running them, also enabling IPv4, IPv6, and DNSSEC in those servers. So that's what you will be capable of doing after this 5 presentation series. Thanks.
exactly. Great. Thank you so much, everybody. We will keep the evaluation form on for some more minutes. And if you already done the answers, you are good to go. See you next month. Enjoy the week.
Bye-bye.
Thank you,
Have
everyone.
a great day and great week. Bye-bye.
Okay, bye.
And enjoy the sun there. Here it's freezing.
We will go there soon.
Face to face, Nico, come on over.
Yeah, yeah, please.